Well, thanks very much for the invitation to give this talk. Unfortunate that we can't all be sort of together in the same venue, but hopefully you'll find this an interesting topic. What I'm going to talk about tonight is looking for anomalies in astronomical data. So looking for features in astronomical data that can't really be explained by natural phenomena. And so one possible explanation could be that these are imprints of advanced civilizations, the technical imprints of advanced civilizations that in principle could be made in astronomical data. And this is particularly the case as our instruments become more and more sensitive and cover more and more of the sky, which is actually what is happening in this particular era of astronomy at this point in time. So let me sort of launch right into the subject. So I think this question is really one of the most important questions that any of us can ask. Are we alone in the universe? I think it's a question that engages just about everyone. I don't think I've ever met anyone who isn't interested in the answer to this question. It's something that I think we've all thought about at some point in our lives, and also have our own ideas and opinions about. And one of the important things is that there's really no real expert in this topic. You can go to the greatest astrophysicist in the world or the greatest biologist, but in fact, everyone has an opinion, and a valid opinion, because no one really is an expert in this topic. If you come to this sort of question from the point of view of a physicist or an astronomer, then you're always impressed by sort of the weight of numbers that are involved. Physicists are often feel very comfortable with this idea of a principle of mediocrity, the Copernican principle. If something has happened here, then if the conditions are the same, then it'll probably happen somewhere else. And if you look at the opportunities that there are for life to arise in our own galaxy, but also in other galaxies, well, we believe there are many opportunities, because we pretty much know now that most stars host planetary systems, just like our own star, the sun does, and that many of those planets will lie within the so-called habitable zone, so that they're not too close to the sun, that the planet's too warm, they're not too far away, that the planet's too cold, but they sit in this nice area, the way our own planet does, where water, for example, is available as a liquid. And so it seems very likely that the conditions for life, just as the conditions for life were met here on this planet around 4 billion years ago, that those conditions probably exist in many places in the Milky Way, but also in many other galaxies in the universe. So from a physicist's point of view, it's a very attractive proposition that if something happened here, then given the same conditions somewhere else in the universe, we expect the same phenomena to arise. So life here sort of implies that life might be elsewhere in the universe. In fact, it might even be widespread in the universe, given the number of planets that have the right conditions for life to potentially arise. Another question, which is rather different, is intelligent life. And again, this is something that we're all interested in. I just put a few sort of interesting concepts that many people have had about what intelligent civilizations might look like elsewhere in the galaxy or elsewhere in the universe. But intelligent life is rather different, I think everyone would agree, from simple life, in the sense that even if simple life is widespread in our own galaxy and in other galaxies, it's not absolutely sure that in particular that a technical civilization, so a civilization capable of communicating across interstellar distances or making itself visible to the rest of the galaxy, it's not absolutely clear that if you have simple life, that eventually you will also have intelligent life. Pretty clear that those two things probably are potentially separate things. And indeed, if you go and talk to a biologist, they will even tell you that potentially, even if you have the right conditions on a planet, that even the most simple sort of single cell life might actually be quite a rare event. It might be a rare combination of events and chemistry and conditions that might not ever be repeated anywhere again in the universe. And you can even take that to intelligent life, where the odds become even more rare. Now, I think we have to have a caveat there that no one actually understands, biologists don't actually understand how life has arisen on this planet. So without really understanding that, it's very easy to think it might be a random event, but there might be some prescriptive aspects of how life arises that actually makes it more likely when you understand the processes behind it. And also, one of the other interesting things that we've kind of has become a bit more clear to us over the last few years is that this idea of panspermia, where life might be transferred from one planet to another planet. Usually we've thought about this in terms of our own solar system. So, for example, we know that Mars and the Earth exchange material all the time because of sort of meteor impacts on the surface of these planets, dislodges material which is beyond the escape velocity of these planets. And eventually, a significant amount of Earth material arrives at Mars and vice versa. And it's possible that life might be able to survive those kind of interplanetary journeys. Another interesting thing is that we've just discovered in the last 3 or 4 years that we also have transfer of material, not just between planets, but actually between one star and another star. So we recently had this interstellar comet or object, Oumuamua, which is believed to have been ejected from one star system and made a close pass of our own solar system. So the idea that life has to originate in a particular planet, we might be able to relax the conditions of the incidence of life by thinking that you can actually spread life, that you can actually distribute it, so that even if it's a very rare event, it only has to happen once before it's distributed amongst the stars. So that just gives you some kind of background about the perspectives of at least scientists in terms of this question: Are we alone? Now, I like this quote by Stephen Hawking, so I'm going to read it out to you. So it says, "To understand the universe, you must know about atoms, about the forces that bind them, the connections of space and time, the birth and death of stars, the dance of galaxies, the secrets of black holes. But that's not enough. These ideas cannot explain everything. They can explain the light of stars, but not the lights that shine from planet Earth. To understand these lights, you must know about life. You must know about minds." And I'm going to come back to this theme again, because I think often astronomers, when they're thinking about understanding the big picture of the universe, that they look outwards and they look upwards and they look backwards in time and they look beyond their own environment and their own circumstances. But in fact, what we have here on this planet, the life that we see around us, the life that has completely modified this planet Earth, these are important aspects also to understand that big picture. Now, I think we all know that technical civilizations modify their environment. We are doing that right now. And in particular, energy-intensive civilizations, so those that are using a lot of energy, a byproduct of that use of energy is to modify their environment. I'm going to give a few examples of how we do that. In particular, if you look at the planet Earth, the one thing that really distinguishes it and makes it rather special is that there's a very significant radio background coming from the planet. And that background is coming from many devices, billions of devices. For example, the mobile phones that you have in your back pocket, or the laptops, or the mobile towers that you see every few kilometers, or all the Wi-Fi systems that are in your houses just now. You're probably sitting in a room that's absolutely permeated by low power radio waves, but there are many of them. So there's a significant radio background that we produce as a technical civilization that would not normally be present on this planet if we were not here and we were not active and we were not a technical civilization. And as you've probably seen, we extend that halo of radio radiation out beyond the Earth's atmosphere. You probably saw this week 120 Starlink satellites launched by SpaceX, all in low Earth orbit. So we have this halo of radio emission that's now extending beyond the surface to low Earth orbit. And already, of course, we have radio communicating satellites in geosynchronous orbit. So we have this low-level radio background, which is very peculiar, very non-natural. And then on top of that, we have a few very powerful signals. So here we're talking about a few very powerful signals associated with communication systems. For example, I just give here the example of the Deep Space Network that connects and communicates with spacecraft on Mars and the outer parts of the solar system, for example. But we also have prolific radio systems like civilian and military radar, which are very powerful and which track commercial and military aircraft. And in addition to that, we have over-the-horizon radar, which tracks the potential launch of intercontinental ballistic missiles. So our planet is really awash with a combination of low-level signals, but many of them, covering a large range of radio frequencies. And then a few typically more focused in terms of their frequency, but very powerful signals, which are being broadcast with very high gain out into space with these very large antennas of these significantly powerful radar systems. And this just gives you an example of the kind of non-natural signal that our own radio telescopes can quite easily pick up. So in the plot here, you see in one axis, the x-axis, you see increasing frequency. On the y-axis, you see increasing time. And you'll see this sort of line of emission. This is the signal, the carrier signal coming from the Pioneer spacecraft that visited the outer parts of the solar system many years ago. And this is the typical characteristic of technology. So what you see is that the signal itself is confined to a very narrow range of frequencies, just a small range of frequencies, and we modify those frequencies, we modulate those frequencies in order to actually send information from the spacecraft to the telescopes here on Earth. So that's one of the sort of telltale signs of technology, especially communication technology, is that the signal is really very narrow. It only occupies a few frequency channels. Then the other thing you'll notice from this plot is that frequency, the peak of the central frequency, is actually changing with time. So the peak in the power of the signal changes as a function of time. And that's because there's a relative velocity between the spacecraft and the radio telescope. For example, the radio telescope is on the Earth, but the Earth is rotating. The spacecraft is also moving away from us. And it's actually that acceleration, the change in velocity between ourselves and the spacecraft, that means that the frequency due to the Doppler effect is continuously changing. So the frequency of that transmitter on the spacecraft continually changes as we view that with our radio telescope. So these are the hallmarks of technology. So we kind of know, at least from our own technology, one signal, which is something that nature does not produce. So typically radio sources that might be associated with planets or with galaxies or quasars or pulsars or whatever, they usually produce very broad radio emission across a very large fraction of the radio part of the electromagnetic spectrum. But technology produces these very narrowband signals. So that makes it interesting to go and look, not just for our own signals on spacecraft, but looking for signals perhaps from other civilizations in distant stars. And we're not just doing this in the radio, we're also thinking about how this phenomena of technology, these techno-signatures as we call them, how those can manifest themselves across the electromagnetic spectrum. But one area that I'm also interested myself is not only in the radio, but also in the mid-infrared. So a little bit higher up in the electromagnetic spectrum, shorter wavelength, higher frequency. We know that we produce on this planet quite a lot of excess mid-infrared emission. And we do that because we produce a lot of waste heat. We produce a lot of waste heat in our houses. Our houses are not totally efficient. A lot of heat escapes from our houses. Our vehicles produce a lot of waste heat. Our factories and our power stations do the same. Our mobile phones, our laptops, these all produce a lot of waste heat. And that introduces an excess in the mid-infrared emission of our planet that would not be there otherwise. If you have a civilization that's doing this on a much larger scale than we do it on this planet, then there's the possibility that our very sensitive infrared telescopes might have the possibility of detecting this excess emission. And as I mentioned before, we're doing this across the electromagnetic spectrum. I'm really going to talk about the left-hand side of this slide, but I also want to note that we're also producing emission on the right-hand side of this slide, although it's probably easier to detect with the technology that we have, at least, the emissions that are being produced on the left-hand side. And so this pursuit of SETI, the search for extraterrestrial intelligence, typically focuses on these three areas, looking for narrowband, high-powered radio emissions, looking for waste heat emission that manifests itself probably in the mid-infrared or the far infrared, looking for an excess in objects in that particular waveband. And then the other area that's also very interesting, but which I won't sort of talk about tonight, is very narrowband optical emission, so laser emission, which could be a very important way to communicate over substantial distances in the future. Again, this is analogous to the radio situation where you have a very bright signal, but it's confined to a few frequencies. So it's actually quite easy to distinguish these from the natural background of stars and galaxies and quasars, etc., etc. So a huge amount has changed in this field of SETI over the last few years, and there are many reasons for that, but I think the major reason for that is what's called the Breakthrough Listen initiative. This is an initiative that's funded by the gentleman that you see there in the top of the screen, Yuri Milner, and his wife, Julia. They have sunk $100 million into the pursuit of using the very best telescopes that are available to them to conduct these very systematic SETI surveys using the best technology that's available to them to do SETI in a way that it's actually never been done before. Not only is it more systematic, but the technology and the back-end technology is many orders of magnitude more capable of what we've had in the past. So this program has had a huge effect. It's been running now for about 5 years, but it's really transformed the field, and the field is active actually across the planet, and the field is active with many, many young people now. So the prospects of actually detecting the SETI signal for these reasons has never actually been any better than it is today. Let me say something about the Breakthrough Listen radio surveys. They also have an optical laser survey, but I'll focus on the radio surveys. Their first survey is to look at the nearest stars, the 1 million nearest stars. It's a survey that's only just started, so they've only started looking at the first few thousand, but hopefully they'll finish that in the next few years. They're using the Parkes radio telescope in Australia and the Green Bank telescope in the United States, and also the Meerkat telescope in South Africa to conduct this survey. And hopefully they'll also be in the future using the JVLA also in the United States. So that's sort of the traditional SETI survey, looking at the nearest stars, but not worrying too much about what kind of stars they are, looking at essentially all spectral types. And then the other survey that's sort of already started and is mostly almost halfway complete is a survey of looking at the center of the Milky Way, where the stellar density is very high. So there's many, many stars if you look towards the center of the Milky Way, and also along the plane of the Milky Way. So good progress has been made there. And also looking at the nearest galaxies. Although galaxies are very far away, the nice thing about galaxies is that you have many, many stars within the field of view of your radio telescope. So if there are any really powerful signals out there, you might just be lucky and find something associated with a distant galaxy or a nearby galaxy. I want to talk about involvement that we've had with the Breakthrough Listen program in Manchester. We've been looking at the first results from the 1 million star survey. As I say, very beautiful, systematic survey using the really best technology. But one thing that they assume, and a thing that SETI researchers have assumed for a long time, is that when they point their radio telescopes at a particular point in the sky, that they're only observing one star. They're just observing the star that's at the center of the field. So they kind of believe that this to be a reality, but this is not the reality. The reality is that the radio telescope is sensitive to actually quite a large area of the sky, something like the size of a full moon. And so what we've been busy doing is actually trying to use that to say that, in fact, SETI surveys can actually put much better limits on the incidence of techno-signatures than we have sort of hitherto supposed. So we've been working on that quite a bit. And this just gives you a sort of pictorial idea of what we are doing. We are saying that we're not just looking at the particular target that we might be interested. We can't help but actually look at all the other stars that are in the field of view of the telescopes. And in the past, it was very difficult to make any use of that fact. But that's really changed with the launch by ESA of a spacecraft called Gaia. And Gaia has used the parallax method to measure the distances of order 2 billion stars in the Milky Way, an enormous number of stars, making a 3-dimensional picture of the Milky Way. Absolutely fantastic mission. And it gives us the distance to many of these stars. And knowing that distance, we can actually put very interesting limits on the incidence of very powerful transmitters, and not just at the vicinity of the target, but within the Milky Way itself. So that's something that we've been doing. We published a paper on this back in September last year. So we've been able to push down the limits on the prevalence of very powerful transmitters. So you'll see a big number there. So 3 times 10 to the 14 watts. That's much more than the energy generation of our own planet at the moment from all the power stations that we have. But you have to remember that you can generate these powers if you have a very large radio telescope with a large gain of maybe 10 to the 6 pointing in a particular direction. So we don't really need to produce those energies, or they, the extraterrestrials, don't need to produce those kind of energies if they're transmitting with a very large telescope. In any case, we're only really sensitive to transmitters that are essentially on all of the time. But within the nearest 600 light years, we can say that less than 0.04% of stars within that distance don't seem to host these kind of transmitters, at least in the frequency ranges that the Breakthrough Listen project is looking at. And that's typically frequencies less than about 10 gigahertz. One thing that's interesting is to extend this further. We haven't done this yet, but that's something that we'll do quite soon. Is not only is the telescope sensitive to stars in our own galaxy, but it's also sensitive to other galaxies. So you can extend this approach. And as I mentioned before, galaxies might be very distant, but you have a lot of them within your field of view. So the numbers of potential extraterrestrials is very high. So statistically, it makes it interesting to look at these objects. In astronomy, we often find that there are a few very, very bright sources and many, many faint sources. So it's possible by looking at a large number of stars, i.e. a large number of galaxies, you might be lucky and detect those very rare but very bright sources. In any case, this is the press release. If you're interested, you can Google it. I just wanted to point out that this is primarily the work of a student of mine, Bart Wodnarczyk-Sroka, and this kind of sums up in a very nice image made by Daniela Futsala what we have been trying to achieve. Now, another thing which has just turned up in the press just a few months ago is that this Breakthrough Listen program, the Million Star Survey, has actually produced its first interesting candidate. Now, I'm not saying that this is an extraterrestrial signal, and they are also not saying that this is an extraterrestrial signal, but this candidate has very interesting properties that I'd like to share with you. The papers have been submitted to a well-known journal, and they're being refereed at the moment. I think the expectation is that these papers, scientific papers, will appear probably within the next month or so. But the candidate was actually leaked in the Guardian newspaper in September. And I just want to sort of share with you some of the properties of that signal. It's a narrowband signal, so exactly what we are looking for in terms of technology, but then everything, all the radio frequency interference that we see is typically narrowband. The central frequency of the signal is drifting, so it's changing with time. This Doppler drift that we expect because the relative velocity between ourselves and the transmitter is likely to be changing. So the frequency will be changing due to the Doppler effect. And another thing which is very interesting is that when you do these SETI observations, you point at the target and then you move to another part of the sky. So you're continually going onto the target, off the target, on the target, off the target. And in these observations, which last a few hours, the signal is only present when the telescope is pointing at our nearest star, Proxima Centauri. So obviously, very interesting. The best candidate, I would say, that we've ever had, much better than the famous WOW signal of 1977, which many of you may be familiar with, which I think is actually a very poor candidate. But here you have sort of the three criteria that you're looking for in a SETI signal. So one problem is that although the signal was present in the data around maybe 1 or 2 days during the point at which the Parkes telescope was observing, the signal has not been redetected again in any other observations. That is actually a very familiar situation because that's familiar to the WOW signal, which has also never been known to repeat. And the bottom line is that the best interpretation of this signal is it's kind of pathological, that it was just really by chance that it was on when the telescope was pointing at Proxima Centauri, and it was off when it was pointing away. Because the careful analysis that the Breakthrough Listen team have done suggests that there are many telltale signs that this signal is actually generated by human-made technology. This is just a picture. This is a lovely presentation that's on YouTube at the moment by Sophia Sheikh, who's the lead author in one of the papers on this system. If you go into YouTube and you search for Breakthrough Discuss 2021, you'll find this presentation. But it just shows you in this plot, again, a bit like the Pioneer 10 plot, you'll see when the signal was on, when it was off, when the telescope moved away from Proxima Centauri, then it moved back, it was on again. So really sort of quite an interesting signal. I don't want to go into the details because we don't have enough time, but they have concluded that it is being generated by technology, probably located within a few tens, maybe a few hundreds of kilometers of the telescope. Some of the reasons that they believe this is that signals similar to this signal have been observed on other days, and they don't go away when you move the telescope on and off. And there's also signals similar to BLC1 that appear at other frequencies, but the frequencies are actually related to the frequency of BLC1. So it looks as though there's some products of intermodulation being produced somewhere that have produced this signal. And also the apparent frequency drift of the signal is quite hard to understand. Its magnitude, etc., doesn't really correspond to what you might expect from any transmitter at the location of Proxima Centauri. And it actually has all the hallmarks of a sort of cheap transmitting device that's sensitive to changes in the temperature. And those changes to temperature actually change the central sort of frequency at which most of the power is emitted. So it's probably that rather than any Doppler drift. The point that I want to make actually is that this is probably one of many Breakthrough Listen candidates. So far there's only been a few thousand sources, actually stars observed. So already we have one rather interesting candidate. But you can imagine that when you've surveyed 1 million sources, there will be thousands of candidates that these surveys are going to generate. And many of them will be just like this signal, just like the WOW signal. They'll be ambiguous, they may well be one-off events, and they may be very difficult to substantiate with follow-up observations. And the other point that I want to make, and this is a big limitation of single dish telescopes, and it goes back to the point that I made earlier, is that even although you're pointing at Proxima Centauri, and even though this is the nearest star, well within the neighborhood of the sun, the signal, if it was a real signal, could be coming from any of these stars in the field of view. So tens of thousands, in fact, many more than tens of thousands of stars could actually be the location of that transmitter. And in astronomy, without really being able to pinpoint the location of a source, I think what you can do is actually somewhat limited in many ways. You want to be able to associate a phenomena with something else on the sky. For example, the position of a star or the position of an exoplanet, etc. So really, we can do much better than this. And one of the ways that we can do better is not just to use a single telescope, but to use 3 or 4 of them and to separate them in distance by hundreds or even thousands of kilometers. That would mean that any local interference that is maybe only detectable on a range of maybe 100 kilometers will only be detectable at one telescope rather than all of the telescopes. A real artificial extraterrestrial signal should be detectable by all of the telescopes, not just one individual telescopes. And not only by observing simultaneously, but actually using this technique of interferometry, where we multiply the data between every possible sort of telescope pair. We correlate the data we multiply the signals together, looking for a correlation between those signals. When we do that, we can do even better in terms of reducing this radio frequency interference problem. And in addition to that, we'll have many independent detections of a potential SETI candidate. So, for example, we have 4 telescopes here, so we have 6 independent interferometer detections, and we should detect that signal on all 6 baselines. And that would be really very impressive. That would really tell us that we were looking at a signal that was beyond our own planet, that was really out there in space. And another thing that an interferometer allows you to do, especially one that's extended on scales of 1,000 kilometers or more, is that you can pinpoint the location of that signal. So you would know exactly where the signal is coming from, whether it's a star or a galaxy or an exoplanet. You'll be able to do that with interferometry, at least within our own Milky Way galaxy. And we'd also be able to detect motion. So, for example, if the transmitter was located on a planet and the planet was orbiting around a star, just like the Earth orbits around the sun, then we would see the motion of the transmitter, and we'd see that really quite easily. If the transmitter is located on a moving platform, for example, a spacecraft, certainly if it's traveling relativistically, or even not relativistically, but at some small fraction of the speed of light, we could detect that within a few days, the movement of the transmitter. And even a very slow spacecraft like our Pioneer spacecraft, we could detect motions of that within 1 kiloparsec, so that's about 3,000 light years. We'd be able to detect that motion on timescales of about a year. So I believe that Breakthrough Listen is doing fantastic stuff, but we can extend it and we can do even better stuff, especially follow-up observations of interesting candidates using radio interferometers rather than single dishes. I want to move on to anomalies in astronomical data. I like this quote by Arthur C. Clarke, who I'm sure many of you are familiar with. And this is Clarke's third law. Any sufficiently advanced technology is indistinguishable from magic. So it's basically saying that, if you have an advanced civilization, they can do things that we would consider sort of unnatural. And we can think of ourselves, the technology that we have even today compared to the technology of 100 years also looks like magic. Being able to communicate in the way that we are doing right now at this moment for someone who was maybe born, in 1910 or whatever, this would be almost a form of magic that we are quite familiar with today. So looking for astronomical anomalies is a little bit looking for these things that we really don't understand. And I want to give you kind of a brief summary of some of the things we've been looking for. We've covered sort of these narrowband radio signals with the Breakthrough Listen program, but also looking for the transits, looking for things that go in front of stars and change the light output of stars. So if you have a large megastructure going in front of a star, might be a Dyson sphere or part of a Dyson sphere, for example, then you can see dips in the light curve that are much larger than any dip that you would associate with an exoplanet, for example. So they're much deeper, but they will also be asymmetric if the structures are asymmetric, which you might expect for technology. So that's one thing that people are looking for at the moment. And there's one particular example known as Boyle's star, where we've seen these dips, but it looks as though it's not technology, but it's some sort of dust-like phenomenon. Then there's looking for things like extreme proper motions. Because we're really embarking on doing huge surveys of the sky, Gaia, for example, is a good example. We can look for these sort of strange objects that are going really fast. They're very difficult to actually pick out, especially with sort of standard pipelines. But if we look at the data, we might be able to determine extreme proper motions or non-Keplerian dynamics, for example, the kind of dynamics that Avi Loeb has suggested for the Oumuamua interstellar comet asteroid. Another thing that's interesting is that you can measure distances to stars in different ways. You have spectroscopic distance measurements, you have geometric distance measurements, that the type that Gaia does. And if you found that these for the same star were very different, then that might be because there's a lot of obscuration around the star. Again, thinking about these Dyson spheres that have been hypothesized for over 70 years, that might be collecting energy from a star in order to power a advanced technical civilization. So these are the other things that you can look at. Things that are just really unnatural, and unnatural patterns in the sky. If you go out tonight and it's a clear sky, you will be able to detect a techno-signature in that sky. It's called Starlink. It's the SpaceX Wi-Fi project. 120 satellites launched just this week, and you'll find them traversing the sky basically in a line. So we're looking for those kind of unnatural patterns, for variability in objects, stars that disappear. For example, there's a project looking at that at the moment, and stars shouldn't really disappear. Even on fairly long time scales, they should be around and they should be fairly constant, but they shouldn't certainly disappear. Or also just interesting clustering effects that appear to be non-natural. And last but not least, and the thing that I want to talk about, which is part of some of the stuff that we're doing in Manchester, is also looking for galaxies, for example. The idea that civilizations might actually be able to harness a large fraction of the energy output of a galaxy. That would change the sort of spectral energy distribution of the galaxy. It might appear excessively bright in some bands and much less bright in other bands. For example, again, in the mid-infrared, they might appear very bright compared to other wave bands, for example, the radio. So that's one of the things we've been doing in Manchester recently. I've been doing this with a PhD student. Galaxies, typically they follow fairly broad scaling laws. So there's sort of relationships, fairly tight relationships between the mass of the galaxy, the size of the galaxy, its luminosity, the sort of colors, the spectral energy distribution of a galaxy. These are sort of fairly broadly the same, especially for different galaxy classes. And there's one sort of fundamental correlation between the emission that a galaxy produces in the infrared and in the radio. Essentially, the infrared, at least the mid-infrared, is roughly about 10 times as luminous as the radio. The far infrared is roughly about 100 times more luminous than the radio. And the reason that there's this correlation is because in these galaxies, both the radio emission and the infrared emission, typically, is produced by massive star formation. So we see this correlation come out every time when we're looking at many, many galaxies. And it happens to be a very tight correlation. And it doesn't just apply in the local universe, it actually applies at cosmological distances, which is also very interesting. So I've been doing this with a student, Hong-Ying Chen. I just submitted the paper to monthly notices. Don't worry about the axes here. It's basically the fact that you have all these red dots all in the same place is telling you that there's a correlation between the mid-infrared and the radio. So most of the galaxies lie in this region across the middle of the plot, and these are sort of normal star-forming galaxies, or even vigorously star-forming galaxies, or even mildly active active galaxies fall within this band. Down at the bottom, these outliers at the bottom, we kind of know what these are as well. So these are typically what we call active galaxies, radio-loud galaxies. And they have much more radio than you would expect from a normal galaxy, because there's accretion of matter onto a black hole, and that black hole launches very bright radio jets from its accretion disk. And that produces a lot of radio emission. So we know what these objects are as well. What we don't expect is outliers at the top of the plot. There's no real reason that we know of, at least in large numbers, why there should be objects at the top of this plot, at least from natural natural phenomena in the universe. But if you consider Kardashev type 3 civilizations. So these are the civilizations that are able to harness a large fraction of their the energy content of their galaxies, so the energy from stars in their galaxies. This is the area that they would occupy. So we've been looking for examples of that, looking at those sources that do have these very high sort of ratios of mid-infrared to radio emission, trying to understand what they are. And so far, we've concluded that they're all completely natural, that there's no reason to invoke Kardashev type 3 civilizations, which is a bit disappointing, really. We've looked at 16,000 galaxies so far. We can actually, in the future, we'll be able to look at millions of galaxies for this phenomenon, but so far we've been rather disappointed. And this whole area of astronomical anomalies is just going to absolutely expand hugely. Astronomy is very much going to a sort of survey instruments that are able to map instantaneously sort of huge areas of sky. They will produce many things that we don't understand every night. There will be millions of objects that these telescopes are producing. And we'll need to be using not just our own eyes and our own brains, we will need to be using the brains of machines, artificial intelligence and machine learning in order to actually be able to harness the science from what all these wonderful instruments are going to produce. And some of these anomalies might possibly be due to extraterrestrials. We have to have an open mind to that possibility. So I want to be rather critical of my own field at the moment. Of course, I'm an astronomer. I sometimes think that astronomers can be kind of guilty of working in splendid isolation, that we just look out there. We look upwards. We always look backwards in time, typically, especially observers. We don't really look too much about what's around us and what's happening. We almost feel as though astronomy is so special. It only happens, 200 kilometers and above, or even 200,000 kilometers and above. But the reality is that what we see around us here on this planet, that's actually telling us the big picture as well. The fact that there's life on this planet, the fact that that life has transformed this planet would not look the way it does, except for the fact that life has taken a hold of the planet and completely transformed it. And we are doing, as a species, humankind is doing exactly the same thing at this moment. We can't ignore that fact. We can't just look outwards all the time. We have to see the really big picture and use all the information that we have. And so there's a kind of tension in astronomy. And I just want to sort of a quote here from Shklovsky, who's one of the great astrophysicists of the 1960s. And he sort of set the standard for the way astronomers think, especially about SETI. And that is, any phenomena should not be declared artificial before all the natural explanations have been completely exhausted. I would say that's a typical astronomer's view of the universe and a typical astronomer's view of SETI, and I don't completely disagree with it, but I do think we have to have an open mind. And I would like to point out that the student of Shklovsky, who was Kardashev, the same Kardashev we spoke about earlier, had a very different viewpoint. He said, the presumption of naturality of every astronomical object is coercion over creativity. Each scientist has the right to work within the framework of their belief system and intuition. So there's a kind of tension in astronomy between these two, and sometimes it manifests itself in ways that are not always completely pleasant. But I think we do need to recognize it. And I think as astronomers, we do need to be as open as possible, especially as we're going to be inundated with all these anomalies over the next decade or so. And I like cartoons, and I think maybe this cartoon kind of sums it up, that we can be overly focused. And sometimes, we can be focused on particular objects, maybe it's gravitational lenses or pulsars or exoplanets or whatever. And we need to see, as astronomers, we need to see the big picture. We need to keep our minds open to all possibilities. So I want to go into some speculative thinking. This is the point at which I probably get fired from my job, but I want to do it anyway because I got to the point where I'm old enough that, well, if they fire me, it probably doesn't matter too much anyway. I like this quote by Carl Sagan. We are a way for the universe to know itself. I'm not sure that I actually agree with it, but it's sort of an interesting thought that sort of humans have been put here in this universe to try and understand how it works. For the universe itself to understand what it is, it needs intelligence. And, you know, we are obviously the height of intelligence. So this is a interesting quote, although again, I'm not really sure I agree with it. In particular, I'm not sure humans are really up to the job of detecting other civilizations. I think we have very prescribed ideas about what it is that we're looking for. Radio astronomers are a very good example of it. Radio SETI is an excellent example of it. But if we have machines doing this work, if we have artificial intelligence and machine intelligence and the algorithms that are organic almost, in the sense that we don't have full control over them, we may get beyond these biases that we have. And surely the amount of data being produced by these new astronomical facilities will need this approach. There's no way that humans can make sense of all the data that will stream from all the telescopes across the electromagnetic spectrum in the next decade. In fact, it's already the case certainly in the radio domain. This is already the case. So it could be that in the end, it's actually our machines searching for their machines. It could well be that biology just has this propensity to produce machine intelligence. We see this happening now. In 100 years' time, if our civilization is still ongoing, it seems to me that there's every prospect that machines will be intelligent, that they will be able to do many things, they will appear at least to think for themselves, that they will be creative scientifically. So we need to bear this in mind. And if we think what things might be like 1,000 years ahead, then anything is possible. I want to just also, before I go into the speculation, think about how an astronomer thinks about the universe. I think this plot, I just kind of drew it up very quickly today, but it's kind of the history of the universe in a nutshell. For a lot of astronomers, this is it, in fact, most of them are not very interested in what happens on the right-hand side, in terms of what happens on this planet. Most astronomers deal with what happens on the left-hand side. And of course, it's looking in the past because that's what telescopes do. They look into the past. Typically, they're not really looking into the future. You need theorists to do that. But if you do think about the future, and I think we need to think about the future a lot more, one thing that's absolutely clear is that even in the locality of this little solar system, which is just a speck of dust in the scheme of this universe, there's at least 8 billion years of history still to come. And if you look at the previous 13 billion years, you see the interesting things that have happened then. Who would say that interesting things will not happen in the future? We know from astronomy that certain things will happen, and these are listed here. The fact that Mars will come in the habitable zone about 1 billion years from today is very interesting. The fact that the ice on the moons of the outer planets will be melting at the time in which the sun comes to the end of its life. All these things produce possibilities. Maybe not many possibilities on the Earth in a few billion years' time because life is likely to be extinct. But certainly elsewhere in the solar system, interesting things will be happening. And they may well be as interesting as all the marvelous things that have happened in the last 13 billion years. So going back to that Carl Sagan quote, one can speculate whether human beings are the only entities that can make sense of this universe. That we know that there's biological intelligence. It looks as though it's branching off into something that we currently call machine intelligence. Who knows where that will go in 1,000 years? But there may be other completely independent branches of intelligence that may not yet have formed, may form in the future evolution of the universe. But I think we have to be open to these ideas if we want to be able to have the broadest perspective in this pursuit of answering the question of are we alone? And I like this quote by Thomas Hardy. While much is too strange to be believed, nothing is too strange to have happened. So I like this idea of a tree of intelligence with its basis in cosmic foundations, but with all sorts of possibilities in the past, but also in the future of the universe. So just wrapping up, I just want to, last few slides, I think SETI expands our minds. It makes us question things that typically as astronomers we don't often think about. So for example, that Copernican principle is deeply rooted in physicists, deeply rooted in astronomers. And you know, it has served us well over hundreds of years, this idea of the principle of mediocrity. In 1960s, you know, we didn't know if there were planets around other stars. All we knew was that there were planets around our own star, and we assumed that, well, that's probably the same for other stars. And we were absolutely right. Principle of mediocrity absolutely hits that on the nail. But when it comes to life, and when it comes to intelligent life, and when it comes to technical civilizations, we do need to ask the question, is there something special about this planet? Now, I don't believe it, but I think it's a question that we need to ask and we need to think about. In the near future, we know that we have plenty of challenges facing humans. If this is a rare event, if our planet is sort of the 1 in 10 to the 23 possibilities where this kind of complexity arises, then we'd be well to try and preserve it. And we're facing many challenges in the future. I won't go into the details here, but you're almost certainly all aware of them, not just in the next 1,000 years, but in the next 100 years. We are using resources in an unsustainable way. We're all used to exponentials due to the COVID virus. Well, we have exponentials in the way that we use resources. And just like COVID, if we continue in this fashion, something drastic will happen. So we need to take better care of our planet. We need to think about sustainability. And I think SETI makes us think about these things, because the longevity of a civilization is very much intertwined with the prospects of detecting other civilizations. The lifetime of a civilization, the longer it is, the more likely we are to detect other signals. So we think about these things. Sustainability is clearly important. We have to look after each other. And it's not just our friends and our families. We are on this fantastic spaceship. This is the best cosmic spaceship, the planet Earth, that you can ever think of. And if we don't begin to understand how we can, in an equitable way, share the resources and move forward into a fantastic future of a further 8 billion years just in our own solar system, then I think that would be extremely disappointing. So I'm going to leave it there. Thank you for coming this evening. I hope you've enjoyed the talk, and I'm happy to take any questions that you might have. And I'll just leave you with a summary slide of the talk. Thank you.
Thank you very much, Michael. And I'll take questions from the chat channel now. I'll give each person a chance to read their question out. So I'm going back to the beginning now. And the first question is from Margaret Townley. Would you like to unmute and ask?
Yes, thank you. Brilliant, fascinating, wonderful talk. And all new to a complete amateur like me. But the breakthrough listening was fascinating and very exciting. But I rather in the spirit of your penultimate theme, I loved the last theme about sustainability and looking after this planet. but in the previous theme about the spirit of that we may be we may be wrongly focused or too narrowly focused on the sort of breakthrough listening SETI possibilities. Would it not be sensible and interesting for us to put a lot of energy into getting to Europa, or exploring a great deal more about Europa? Forget about Mars, that's a bit barren and unexciting. You know, let's get to Europa, where there's this sea underneath this covering of ice. Would that not be worthwhile to pursue?
Well, I think absolutely. I think, you know, any way that you can bring some clarity to this question of whether there's life elsewhere is a useful thing to do. So I wouldn't say stop exploring Mars, because, you know, if you go far enough down underneath the surface of Mars, then very likely there's liquid water there, because it gets warmer as you go further down into the surface of Mars. So I wouldn't completely rule Mars out as a place for life. But I think the point you make is a very useful one. Looking at the moons of Jupiter and the moons of Saturn, the ones that have, you know, these huge reservoirs of water on them, that is very interesting, and also sort of quite accessible in the sense that there's often breaks in the ice where the sort of steam, the water, is allowed to escape, so that you don't even need to go to the surface of these planets to analyze the water. You can actually just make a pass along the surface, and you'll detect water molecules and whatever else might be there. Certainly there'll be interesting organics there, but there might be even something, as you imply, something even more interesting. In fact, the Breakthrough Foundation has been funding ideas about how to do this. So I should say that the Breakthrough Foundation, Breakthrough Listen, is only one of their programs. They're also very much looking towards planetary exploration to answer this question about life in the universe. So no, I think it's an idea. It's also an idea, of course, that the space agencies have. NASA and ESA are both planning missions like that. Also, potentially in the future, looking at submersibles that would be able to somehow get below the surface of the ice and go underneath into the liquid water, which would be, you know, so exciting. I have to say, I mean, I agree with your you know, you talked about Mars being barren, and I absolutely agree with you. You know, the first time I saw a picture of Mars, which was when I was 12 years old back in 1976 from the Viking lander, I was so disappointed by that, you know, and nothing has changed. And I know that planetary scientists, and especially astrobiologists, will really not be happy to hear that. But it doesn't do much for me either. But I think, you know, even if there's no life, going into the ocean of the outer of the moons of the outer planets, that must be exciting at some level. I'm just absolutely sure it must be.
Thank you.
Jeff Parks, would you like to ask your question? Well, we're not hearing from Jeff. I'll read the question out. Would it be useful to examine all our own Earth signatures from orbit or at a distance? So that, would that help us to weed out our own interference from candidate signatures?
Yeah, it's a good question. The answer is definitely yes. The experiment has been performed at some level. So in 1993, you may remember the Galileo spacecraft, which was launched via the space shuttle and the IUS. It had to actually make a very close pass to the Earth in order to be able to have the right velocity to get to Jupiter. So Galileo made a close approach to our planet, And it looked at it with all the sensors that it had. Now, it obviously wasn't covering all of the electromagnetic spectrum, but it was covering sort of areas like very low radio frequencies and in the near infrared domain and the optical domain. And it gave us a very interesting idea. There's a nice paper in Nature by Carol Sagan and other authors. The most obvious signature of technology is the radio emission, just because you can't understand why a planet would be producing radio emission over very discrete frequencies, especially very low frequencies, as it does. So the radio stuff was, absolutely clear that when people looked at the data, that this is artificial. But the other stuff that's there is, of course, the atmospheric emission and absorption that's associated with water and carbon dioxide and methane, which is certainly a biosignature, a signature of biology, oxygen, which is a signature probably of photosynthesis, although you can't rule out that some of these things are not being produced by geology. But certainly oxygen won't last very long in the atmosphere unless it's being continuously produced, because it reacts with everything that it comes into contact with. So that experiment has partially been done, the one that you're talking about, and I think it gave great insight into the kind of things that we should be looking for, both techno-signatures and biosignatures from other planets, from exoplanets. If you talk about, being in space and being able to sort of categorize all the, for example, the radio interference, that's probably a bit more difficult, because that radio frequency interference is continually evolving. It's very transitory. It comes and it goes. It's changing on, sub-second levels. So a global perspective there is quite interesting in some ways, and in many ways we actually want to do that. But whether it would actually advance sort of radio SETI surveys, for example, I don't think it would.
Right, Charles Draper.
Hi, great talk. I loved it. I loved the technical stuff and the speculative stuff at the end. If I can cheat slightly on the speculative stuff, it seems to me that our planet story is of green slime as soon as possible, and then billions and billions of years, nothing else, and then complex stuff. And where our planet looks different is, of course, we have a double planet system with the moon being so big compared to. So that's the obvious thing where the Earth doesn't look mediocre compared to the planets we know about elsewhere. That's the comment. The question is going back to the sort of signal to noise ratio business. Mm-hmm. You talked about, if you had some instrument looking out into space, it can see into far distant galaxies too. But surely there must be an issue about the extent to which any visible sign of deliberate production of radiation or emission of radiation would just be swamped by the background, sort of black body radiation. So would it be likely that a sort of a single civilization based on one star system could be detectable in a different galaxy? I'd always thought there's sort of a sphere of detectability involved here.
I think it's speculative to be able to detect emission from a single stellar system, but you can kind of get around the background problem if you put a lot of power into a few frequency channels. So the kind of thing that we actually do in radio all the time, the kind of thing that we do with laser transmissions, is to put as much power as possible into just a few frequency channels, because nature spreads its power across essentially the whole electromagnetic spectrum, and technology has the possibility of doing the exact opposite of that. So you still undoubtedly need, even with a very, very large aperture, so an aperture that can give you a lot of gain in a particular direction. So you would need a lot of power. You'd need a huge aperture, probably a distributed aperture. the radio, but also in the optical, even the laser system. It would have to be made coherent in some way. It'd have to be distributed coherently to the different elements of the transmitter. So I think from our technology perspective, it's pretty difficult. I think you're right, but it's probably not impossible to do it. And if you also think about things like Dyson spheres, I don't think we can detect Dyson spheres even in our own galaxy from single stars at the moment. It would be really not quite difficult, but not impossible, at least for more distant stars. But there you're talking about broadband emission, and you're looking again to see if there's an excess above the thermal emission that all the stars, the star itself and the planets around it are producing. But I think that those things are possible within our galaxy. When you start talking about going to other galaxies, that it becomes, 12 orders of magnitude more difficult. Yes. So you have a good point.
Thank you.
Michelle Hussey, would you like to ask your question?
Hi, sorry, just one second. Hi, say hello. Hi, Mike. So I probably could have just asked you this in work at some point. I do work for transparency, but it seems like a really nice opportunity to raise the question. I'm really interested in the verification of sources. So when is something actually verified, kind of practically here on Earth? What is the consensus and the final agreement where it is declared that something is unknown and something that's new to us here on Earth?
Do you mean in terms of a discovery, or do you mean in terms
So if we, when you were saying earlier on about the recent candidate, the interesting candidate, and then there's obviously varying opinions on that. When is it settled that something that is found is potentially something, or, well, take out potentially, so is something that is completely unknown?
Yeah, so I think, so in the case of SETI, there's supposed to be the so-called SETI detection protocols, so that if you find an interesting signal, you're supposed to analyze it as much as you possibly can, try and think of all the reasons why it's not an artificial signal. And if at some point you've done all possible tests and you basically say, well, look, this just looks like the real thing, then at that point, what you should do is you should ask another observatory to verify it. So you should ask another observatory to observe the same point in the sky at the same frequency and see what the results are. And hopefully they would agree. And of course, the further away the observatory is, as I kind of mentioned earlier, the better. So, and probably you would do that with multiple observatories all across the world, and hopefully they'd all detect the same thing. So that's certainly part of the process of verification. And then the other thing that's part of the verification is that you would write that up as a paper, you would submit it to a journal, and it would be peer reviewed, by your peers before it would become a sort of bona fide publication. So that's a sort of another phase of verification that would come after that. So at least in SETI, that's the way it's supposed to work. It's sort of in science in general. I guess something's sort of verified again when it appears in a paper, when it's published, so it's peer reviewed and published, when other people repeat the experiment and get the same results, that adds strength to the discovery. And at some point, it kind of appears in school textbooks, right? So that's when you really know that it's sort of accepted by the community, or in university textbooks, so that it's accepted by the community. So that's kind of the process. The process really has to be independent verification and peer review.
So it's treated in the same way, in the same method, basically, as any other type of work, any other data. Okay, yeah, no, that's great. Thank you. Thanks.
Okay, can we go to Chris Garcia now?
Thank you very much. Very interesting presentation. I was just struck that the majority of our transmissions emanating from the Earth are because of inefficiencies in our activities. So excess heat, excess X-rays. If we've got radio transmissions leaving the Earth, it's not because we're aiming up there, it's because it's escaped. So I just wondered whether there might be a correlation between the advancement of civilizations and therefore a reduction in the impact they make on that radiation spectrum that you put up right at the beginning, and therefore actually finding the evidence of advanced civilization actually becomes more difficult the more advanced they are. So actually the number of civilizations that are actually making transmissions inefficiently will be quite narrow because of it's only at a particular point in time in their development when they're inefficient like we are.
Yeah, I think I agree with you at some level. Yeah, I think we all have our own experience. You know, if you bought a laptop, for example, 10 years ago and you had it on your lap, you could probably have it there for only an hour before it became so hot that it just became unbearable. And I don't think that's true nowadays. So it's clear that dissipation of heat and the usage of energy has become more efficient in most of our devices, like laptops, mobile phones, computers in general. But there comes a point at which going to, you know, especially if you introduce radiators or you introduce fans, etc., which is what most of these things are doing, there comes a point at which you still will produce excess heat, and it will cost you more energy actually to reduce that than it will to just let it happen. It's just kind of a fundamental aspect of thermodynamics. So it actually becomes very costly to reduce it beyond a certain level. But certainly, I think when you're producing copious amounts of waste heat, there are ways, easy ways to reduce that. But at some level, you're always going to have inefficiency. You're always going to have, you know, when you go from a sort of concentrated form of energy and you do work on it, like in your laptop, it always emerges as sort of a less concentrated, less energetic form than it initially was. It's just thermodynamics, and to cut that out completely is really sort of cost effectively. That's really very difficult. So I think there will always be excess heat, but indeed, a really advanced civilization probably is much more efficient than we are. So probably much more difficult to detect at some level. I think that's true.
Right, Ben MC. Ben MC asks, how challenging do things like Starlink make your work?
So I'm not an expert. Wouldn't claim to be an expert in this area, but I know many people who are. I think it is going to be it's going to make astronomy much more difficult, and it's not just sort of optical astronomy. The fact that we can see this thing with our eyes. It's also, I think, in particular in the infrared, it's very difficult to make these objects, just for some of the reasons we were talking about before. It's very difficult to make these objects less bright in the infrared part of the spectrum. They are obviously using radio emission to communicate around about 10 gigahertz. That's a frequency which is used by radio astronomers in particular. It's a standard frequency for the square kilometre array. in the future. So yes, I think it's going to make things really difficult. It's probably one of the reasons that we need artificial intelligence, is basically to weed all of this rubbish out of the data. So, you know, I think there's obviously a case for these kind of systems, although I'm not completely convinced, but I don't know much about these Wi-Fi systems. I think people will make a great deal of money out of these systems. I would like to think that they would put a small fraction of those systems back into astronomy, because they will certainly destroy a significant fraction of the night sky. And that will have an effect, especially on these big survey instruments that I mentioned before, that are covering large areas of the sky. You know, there will always be one of these satellites here and there within a data set. So it wouldn't be an occasional thing. It'll be a thing that we have to try and extract from the data. And yeah, I think it's a serious problem. And people are thinking about it, but at some level, there are some things that, in the optical, you can make them dark, or you can make them darker. I think when you're in the infrared, it's much more difficult to make them dark, and they're already radio bright just by their nature. So it is a challenge, and it's a very worrying development, especially as Starlink is just the first. There's OneWeb, which is funded mostly by the UK government. You can imagine that China will do something probably even in a bigger scale. So the future may well be that we have to move into space to do astronomy.
Yes, I was going to ask if, based on that sort of problem, would the far side of the moon be a good location for doing this kind of astronomy?
Yeah, far side's a wonderful place to do any kind of astronomy, but it's just very expensive to get there. We're lucky we can do a lot of astronomy from the ground. We need to go into space for certain things, for example, the ultraviolet. There's benefits, obviously, of getting above the atmosphere in the near infrared and in the optical. You need to be above the atmosphere for the X-rays. You need to be above the ionosphere for very low frequency radio work. So the moon is a very interesting place to go. It's shielded from all the emission that's coming from the Earth. But I'm afraid by the time we get there, especially for radio astronomy, that there'll be many spacecraft. The Chinese already have a spacecraft in orbit around the moon that is transmitting at 2.3 and 8.4 gigahertz, and that's just the start of things. So there's a very sort of short window in which the moon might be an interesting place to do things.
Right. Can we go to Roger Moses, please?
Yeah, we're currently moving from broad transmitting systems to closed optical fiber networks for a lot of power communications. We're encrypting everything, which makes it impossible to find out what pieces of communications are. Are we removing ourselves from the problem?
I think at some level we probably are. Optical links are being used a lot, but at the same time, obviously communication has evolved. So in the 1980s, one of the things that made us sort of very bright in terms of techno-signatures was high-power TV transmitters. So we don't really have that any longer. Most TV's been, at least in Europe, has been transmitted by cable. And often for networking, we're using optical fibers. Obviously, there are some things like mobile devices which are not on fixed links. So they're using radio waves, but they're using very low-powered radio waves. So that gives us a radio background. The fact that things are being encrypted so that they cannot be detected is another thing that probably makes things more difficult. some of these broadband systems have cyclical systems that you could look to try and detect from a SETI perspective. But I think it's a fair point. A lot of use has been made of optical links and digitization of data on other systems that will reduce our signature at some level. But there's probably other things coming that will make us brighter, and the waste heat excess is certainly one of those. So that will, if we continue to use energy at the rate that we do at the moment, then within 200 years, global warming will actually be due to excess heat. So not to the fact that we have carbon dioxide and the greenhouse effect, but it will actually be due to the fact that we're just generating a lot of heat from all the devices that we operate. So things evolve and change, and we may become less bright and we may become less obvious, but technologies often, I think, sometimes also do the reverse of that. But I think I take your point, and I think it's a good one.
Well, we've reached 9 o'clock now. Sorry, Roger, was there something else you wanted to say?
Yeah, just a quick point. I mean, 40 years ago, on a cosmic ray satellite that I was involved with, the first thing we discovered were the ballistic missile radars.
Mm-hmm.
Although the spacecraft had ostensibly been proofed against electromagnetic interference to whatever level it would meet, but we found the Russian and American long-range radars okay,
yeah,
and had to remove our data whenever it went through the beams.
Yeah, and those radar systems are still more or less operating in the same way that they did in the past.
Right, well, we've come to 9 o'clock, which is when we have to end. And I'd like to say this has been a really fantastic journey through all the different techniques that are being used to carry out SETI. And in particular, there's a lot of promise in the future with long baseline interferometry and the help of assistance of machine learning to digest the vast amounts of data that this is likely to generate. So it's opening up a field which is very exciting and full of future. And thank you very much for your lecture. Now, if everyone would like to unmute, we can give a conventional round of applause.
Thank you very much. It's been a pleasure to be here, and I wish you all a very pleasant evening.
Thank you very much indeed.